Hi, welcome back to Book Club. Again, we're in Rocket Propulsion Elements by Sutton and Biblarz, and this is a great book. So make sure you're reading it along. I'm here to just, provide some color commentary and kind of the wave tops of the stuff, and for you guys to kind of dig in and really read this fantastic book. Okay, so today we're actually covering two chapters, 10 and 11, this turbopumps and kind of systems. Now we've talked a lot about combustion and the engines and some of the heritage, and so we're really going to start off and talk about turbopumps. Now, the big part on turbopumps is, of course, there's the pressure that you're trying to get to, for sure. This is how you're doing it. Now, we've talked about how you would drive it from a the system point of view, get gas generator or auxiliary stage combustion, kind of all the cycles. But you're ultimately interested in, I'll write it sort of as the change in pressure, your flow rates, but also your aux fuel ratio. We'll see how you end up kind of controlling this at the system level as well. And so there are a couple different things to think through. Now on pumps, the first one off here is sort of a picture. There's a range of pumps. Now the cycles is where the important thing about the cycles is how are you making the hot gases to drive the turbine. The turbine is attached to the pump. But now it's actually on the pump side. So this is the sort of the liquid facing side, where the inlet of the pump is coming from your fuel tank or your aux tank. Okay, and so what you'll see, the main ones you see here are actually centrifugal pumps or axial flow pumps. Okay, a lot of times most rockets I've seen some that are a combination of the two, but centrifugal pumps are not uncommon. Just because how compact they are, and then axial pumps, you see a couple of those. The Spatial-Main engine had some axial pumps and things like that. So the important part here is this figure. You can see the efficiency based on the specific speed. Okay, and so and that's an undimensional number. I think we've covered it previous before. So you can go work through that, and given your design, given these parameters, what is the specific speed, and what pumps you're going to look at. Okay, but honestly, the one of the other really important parts in sort of selecting your speed as well, what really kills your pumps are vibrations. It is non-trivial to build a turbo pump. The bearings, we'll talk through a little bit of how you sort of keep them separated, the fuel and the aux. Okay, and then your big failure modes are really, and I'll kind of switch to orange on that. Okay, it is your bearings that can fail, your cooling of it, right? If it's self-cooled, usually by the aux or by the fuel. Okay, and then just your propellant, cross flow. This is where your propellant ends up going across and talking to it. Okay, drive gas. Gas is usually some side reaction. It is combustion, and so if it's a gas generator, it's going to look a lot different than if it's auxiliary stage combustion, where it's sort of all the aux is flowing through. And then honestly, the you end up doing, and I'll kind of draw it here. So here's an example of actually, I'll try and keep my same consistent thing I was doing last time, where this is sort of the aux pump. Okay, draw it like this. There's aux, and then here's fuel. There's fuel, and this is all sort of connected with a shaft. Okay, so there's a shaft. There's a shaft, and then I'll try and use yellow. It may not show up that differently. The yellow kind of seems the same under these lights, but here's your turbine. Yeah, kind of looks the same. And you have your hot gases driving the turbine. Okay? I know red doesn't always show up well, but sort of driving the turbine is your hot gas. And so this would be example of like a gas generator or something like that. And your fuel is coming in, sort of coming in, and then coming out, and your aux is coming in, coming out. All right. So Uh, one of the things that can happen in that failure mode is if some of these hot gases can kind of make their way back. So that's one bad part. Okay, so there's a failure mode here where these hot gases walk back. Now you've lost some of your cooling. This is getting too hot. But you also have a failure mode here. Usually this common shaft. So it's called your interpropellant seal, or IPS. And that is what is keeping sort of the fuel and ox away from each other. So some designs have it with, you usually have some sort of gas on board, nitrogen or helium. They're using that. Other people just try to drive enough of a labyrinth seal where that mode is really, really, really reduced, so you're not going to see it. So there's a lot that goes into this. Okay. There's also a lot that goes into sort of the bootstrap process. And what bootstrap means is at first you don't have combustion gases because whatever you're driving this, whether it's a gas generator or a stage combustion, that's not operational yet. This engine is at dead cold, and so bootstrapping process usually that's done again with a gas, where you have some that helium or the nitrogen, some sort of bottle, usually like a warm gas that is used to sort of start driving the turbine, and it's not much, but it'll start driving the turbine, which will start pressurizing this, which will then let you open up the valves to that side reaction, which will then drive this more, which will then open up the pressure more, which will then let you, transition into your main combustion chamber, it's combustion. So really it's the whole process, especially the ones that are kind of that staged combustion cycle where you're sort of, all the ox, all the fuel going through. That one gets kind of crazy, right? And so this is a very simple diagram of the Space Shuttle main engine because they had a hydrogen boost pump here. They had a single aux pump. And then you can see here the boost pump's actually powered by some of the exhaust here of the stage combustion. Sorry, it's powered by the high pressure fuel itself. Okay, coming out of the regen, so it's driving the boost pump. So it's sort of a fuel powered boost pump, which is interesting. The fuel comes in here. You get sort of aux rich, fuel rich, aux rich stage combustion, driving both turbines, both sort of the aux turbine here as well as the fuel turbine. And this is actually like the easy diagram. So I actually found online that's actually the legit diagram that shows all the rest of I think it's just the flow paths. So where's your drive gases, your control gases? Most valves are actually pneumatically driven from drive gas, and so you might be like electrically piloted, which means kind of get it. You turn a valve to the nitrogen with electrical thing because it's very small, and then that nitrogen drives a bigger valve, which is actually driving, like opening up your fuel valve or opening up your aux valve. So this can get quite complicated, okay, in a hurry. All right, so kind of back to and then this is actually this came online about a week ago. This is sort of the internet's estimation of the SpaceX Raptor 3 engine. It's actually pretty fun to walk through like what they think and based on pictures and things like that. So I don't believe there's a SpaceX leaker out there, but this is just sort of their estimation of all the fuel systems, and you can see here the legend like cold methane, hot methane, gaseous methane, products, pre-burners, nitrogen, valves. Anyways, I could nerd out on this for a while. So pretty fun. Okay. And oh yeah, it's right here. Let me go back to this diagram. Okay. Specific speed. I actually did write it down. So specific speed is your rotation, and the square root of this is flow rate divided by G delta H to the 3/4. So this is a non-dimensional number. I do have another lecture back on the sort of thermal fluid side on developing non-dimensional numbers if you want to go walk through it. The book does a pretty decent job. But basically, it's just a way to sort of non-dimensionalize your speed versus your flow rates, things like that. So that's what specific speed is, okay? And then your tip speed is the other non-dimensional number, okay? And that is the velocity, your tip speed, and then this is square root of 2g delta h, okay? And usually this is in the range, psi is in the range of 0.9 to 1.1, but ultimately it's really, your tip speed here is just R times omega, if you have that. Okay, and omega is related to n, kind of 2 pi. So these are your parameters that you usually derive your kind of selection and your design points for the turbo machinery. Okay, and so I want to sort of now go into a little bit more systems. So we talked a little bit about bootstrapping, kind of the drive gas, the process. Okay, so this is where then chapter 11 sort of comes in, and honestly kind of walks through like the rest of the story, if you will, sort of all the other things you have to do with a rocket engine. Okay. And so we'll kind of start off here with just sort of listing the propellant uses. And it's not just combustion in the chamber, okay? And so yes, of course, you have your main chamber combustion, yes. But you also, in a lot of designs, thrust vector control, and actually an entire chapter on this towards the end. So this is how you're either pointing the thrust in different directions. Sometimes that's by physically moving the engine. Sometimes it's by deflecting the flame. But it's usually driven by propellant. That's how you do it. Okay. There's a load uncertainty. So it actually, you might think, no, I'll just load exactly this many kilograms. But in order to do that, like when you're loading, you have to have really good mass flow rates. And if it's cryogenic, if you're trying to understand how much cryogen you have in there, you also then have to collect all of the gaseous stuff that's boiling off at some point. So that can be really challenging. So you end up having these load uncertainties that you have to carry from a mission point of view. And so you always want to make sure that at whatever kind of probability distribution you want to have on that you have enough for your mission completion. Okay? Unused propellant. So usually within the tanks, you have some sort of liquid measurement system along the way. And you want that to be lightweight so it's not massive. Again, they're really high accurate but pretty massive systems you can use to measure liquid. Usually what you do is just kind of a small little line in there that's measuring delta P, but there's all of these things you have to do to sort of make sure it's not getting a weird reading. I won't get into more on that. It can be pretty complicated to get your propellant measurement in the rocket while you're going. Okay, and then just margin. So on top of all of this, you want to then have some sort of margin. Now back to OF, which I talked about, and again the picture where you might have ISP and you have some main O to F that you're trying to ride. And you're either looking at the thrust within your system. However, you're getting some sort of estimate of your performance. You actually need the ability to tweak your O to F, and so usually it's some small valve that's either able to add a little bit more fuel or a little bit less fuel, keeping the aux the same in that design, to sort of make sure you can kind of keep on condition. Now, there's also all these other algorithms, which is like for some reason, if I am losing. Let's say you have some leak of aux or some leak of fuel. You need some algorithm that is sort of observing this in flight and then saying, well, guess what? I actually, for some reason, I'm using more aux than normal, and I'm actually then gonna swing over here, and I might lower my ISP a little bit more, but I will make sure I use all of the propellant. I'm not stuck. Again, if I have the loss in aux, I don't want to sort of end my flight with a whole bunch of fuel that I didn't use because that's mass. So some of those algorithmic things are not so simple. Okay, and that's just on the kind of the propellant usage. Okay, and then all the rest of the stuff that you're gonna go into engine design, and a lot of this is you get things like health checks. So an engine may have I'm expecting to see these pressures, I'm expecting to see these temperatures, whatever they are, sort of as you're sort of stepping into different configurations from a cold vehicle to a ready to load propellant vehicle to ready for the mission. So there's all of these things that you will want to do health check wise. You might, if you have TVCs, you might do a wiggle of your TVCs, right? Do some valve clicks while you're dry with your rocket. So there's all of these things you're going to do before you sort of step to the next configuration of the rocket all the way up. Bleed. So you always have to do this. Bleed is where you get all the liquid all the way up to sort of the pump without any bubbles in there, getting rid of all of the gas, air, whatever it happens to be. That's called bleed. And so in order to do that, you have to have a way to, honestly, it's called bleed, like basically dump it off the rocket, if you will, to make sure that's sort of all the way bled in. Now, on your second stage, when you're flying, you have to actually do this while you're flying towards the end of first stage. But you have to think through that whole system to sort of ensure that you have all your liquids up to the point. Now, if it's cryogenic, okay, on top of that, it's called chill, where your cryogens are going to hit the pump, but the pump's warm. It's just going to turn it into gaseous vapor. So you have to have a way to get that gaseous vapor out. Sometimes it can go through the same bleed line, but it's called chilling it in. And then if you have a chill, a lot of times, again, like usually back to turbopumps, your engine might be chilled or the pumps might be chilled, but you might have a go, no-go temperature on, say, the turbine. The turbine can't get down to this certain temperature. So it might be crazy cold here in aux, and it's kind of that conducting is all pretty close together. So you have some of these things that can be go, no-goes. Okay. Let's see what else is there. Whatever your side combustion is for your cycle, it's getting to that ignition process. And I'll walk through a little bit about that. So that's things like spinning the gas and kind of bootstrapping your way up, all the way up until your main combustor is on. And from an ignition point of view, that's like at Virgin Orbit we used TTEB, and I know SpaceX did that a lot on their Falcon 9. I'm not sure what they use for the Raptor engine, but it's sort of a secondary reaction that absolutely burns. So in fact, we would drop, if I remember correctly, it was LOX, and then you would hit it with TTEB, and so you actually get LOX TTEB combustion, because TTEB basically immediately goes, and then you would transition to fuel, and then kind of turn off your TTEB. That's how we would step our way up. Now we did it. The reason we did TTEB is because we were air launched, and so this is a very absolutely guaranteed way of it's going to light. Some other rockets will do electric because you can basically keep holding onto your rocket and kind of sparking. And sometimes you can actually do it from the ground system. You can basically spark from the ground system, and then the rocket can take off, and that ignition system stays on the ground. Usually, if your main stage turns off prematurely, you're usually hosed anyways. Okay. And I mentioned your sort of OF, so you gotta adjust for that as you're flying. And then the last one is stopping. So this is also not the easiest thing to sort of reverse all these processes in a way that are not destructive to the system. And now you may say, like, I don't care if it's destructive. No, yes, in flight, once your engine stops, destructive can mean lots of different things. So you don't want to blow up, but if stopping your engine in a way hurts the engine, you could be like, well, I'm not using it again, unless you're trying to reuse it, like SpaceX will land it. But no, it's actually the fact that when you build an engine, usually you're designing it for an expendable rocket. You're still going to design the engine for 20 starts, because it may take 10 starts for you to sort of prove it out and tweak it on the test stand. Again, sort of making sure you sort of hit all those optimal conditions. And then you usually have some sort of acceptance test that you're going to do. Maybe it's full mission duration. Maybe you're going to like swing all your TVCs. And so usually that might eat up about 10 starts of the engine. And so having a process that is not destructive is actually critical, even if it's an expendable vehicle. Okay. And then all along the way is sort of purges. And this can be to sort of clean out lines, make sure there's nothing in there on a stopping process. Second stage engines usually have to relight. So again, back to orbit, you sort of get to orbit, but you only got to the sort of, your orbit's elliptical. And so you got to actually 45 minutes later on the other side of the Earth burn again to sort of circularize it. So especially on an upper stage engine, you do absolutely have to relight. So you're going to purge all your lines, and you're going to do all the stuff to make sure that you can have a clean engine, kind of almost get back to that cold engine point of view, not this sort of mixed case. And so there's a lot of engineering that comes into it. Okay, and so it's part of what makes it so fun. There's sort of all of the sciencey things, but all of the engineering things to go do all the rest of the things that you have to go do it. And by the way, you have to do this with flight masses and flight engineering, so it can be challenging. All right, so that's it for these two chapters. Again, go read book club. The whole idea here, I'm just saying the wave tops. So you go read the chapters. It's awesome. Dig in, ask me any questions below, and then we'll see you next time.